afternoon, everybody. What was I supposed to talk about? I'm here to give you an update, and just like the previous speaker, I'm not here to sell anything yet. We are Delta Burn. We are an R&D company focused on aero-fluid dynamics. We're registered in a few places around the world, and we do modifications for fan blades and propellers and rotors. Our mission is to drastically reduce the carbon footprint of aviation, and by doing so, to also support the scaling of SAF. SAF, whether we like it or not, is going to be the go-to decarbonization of the next few decades. How are we going to do that? By reducing global fuel burn by 1/3. And in doing so, reducing global emissions by 1/3. And when you do that, you also increase the range of your aircraft drastically. Now, right at this moment, you have two questions. The first question is 33%, 1/3, that's impossible. And then, of course, the second question is why you and why not the OEMs? I'll get into that. In a nutshell, the following is what we do. What you're looking at is a typical gas turbine engine, a turbofan engine, with, the fan, the core, and the bypass duct. What we have here, what we focus on is the efficiency of the fan disc, of the fan blades, and that's the reason why I have one of these up here. We modify the fan blade of the turbofan engine, and by doing so, we greatly increase the mass flow through the bypass duct and also the exhaust velocity. What that does, and I'll show you, this thingy here, take a picture. What it does, it increases the thrust output of the jet engine by around 30%. Again, you think it's impossible, we have to prove. This 30% is not very good for your engine today, so what we'd like you to do is to throttle back and actually use the old thrust, but now at a much lower fuel burn. When you do that, you basically end up with permanently derated engines. Lower operating temperatures, less fuel burn, lower stresses, and also higher safety margins in those same engines that were designed for higher stresses and higher temperatures, but now you're running them at less stress. So how did we get there? We are an R&D company after all. We looked where no one else has looked. We have developed the mathematics behind the aerodynamics that we have discovered, and no, it's not magic, it's real science. We have flight tested this, we have demonstrated this, it's real, it's live. As we are an R&D company, the presentation will have to have a nice slide with lots of lines and circles. If you look at the thick green line at the bottom, that's actually thrust against a percentage of N1. And the effect of what we do is we move that thick green line to the left, where it becomes a violet dotted line, and you can see that we get the same thrust at a much lower N1. We actually eliminate shock waves on your fan blades, and we take that lost energy and we put that at the back of the blade as an additional thrust effector. The fan itself vastly increases its efficiency, around 60%, which is a humongous number. It actually no longer is a more efficient fan, it's a different fan by now. And we do this through what we call elegant aerodynamics. That's all it is, aerodynamics. What we do has never been done before. The theory and the effect itself that we have discovered has been around forever. We were just lucky enough to discover it. Right? In the past, many people looked at this, many PhD papers were written about this. Some of them came close. Nobody reached the end of that particular road. I'm going to show you a takeoff of a 737 Classic with the left engine modified. There we go. So what you're going to see is, so I have to say this at first, the left engine was an old and tired engine. It was burning more fuel and it was running at a higher temperature. So what happens here is the pilot flying is pushing up the throttles to the point where the modified engine and the normal engine are producing the same thrust. This is at the point of brake release. When he's satisfied, you can see that the N1 dials in the middle on the top are showing different numbers, but the thrust of the airplane is equal at this point. You can also see, there he goes, that's the clock, so he just released the brakes, he's going. You can see that the fuel flow dials, the lower ones, there's already quite a gap between the two. Again, while the airplane is accelerating, he keeps adjusting the throttles to maintain that same thrust on both engines. Should be getting airborne by now. Yeah, airspeed is alive, really alive, so gear must be coming up soon. There we go. So now we're flying. I'm going to cut this video short and I'm going to give you a snapshot of the same flight going through flight level 250 during the flight. I took that snapshot myself. This is not AI. This is a real picture. You can see the throttle stagger, you can see the hand on the throttle, and you can see the dials, the left two rows of the stack, clearly showing big deltas between the left engine and the right engine. Because the engine used to run 22 degrees hotter than the right engine and also used to burn 5% more fuel than the right engine, we witnessed this on previous flights. We can make the following story. In total, the fuel flow is 30% down between the modified engine and the non-modified engine. You'll also see that the EGT is more than 100 degrees less. Now just think about that, what that will do to your engines over the life cycle that you're normally looking at. Right? And this was a temporary modification. We modified this engine just before flight in 38 minutes. This is a quick slide about the market, right? Our plan is to basically modify every one of 28,000 air transport aircraft because we want every aircraft to start burning a third less fuel. That's about 50 STCs. I made a quick calculation about how much fuel we actually burn. Actually, nobody really knows. IATA has a number, and then other people have a number. It's tied into how much do we fly, how many aircraft are actually flying, and it's not that easy to get that data. So I took a stab at it, and my number says 120 billion gallons of fuel. That is not just air transport, that includes military, general aviation, and business jets, turboprops, all of it. We will be able to touch 87% of that global fleet, and we will be able to reduce the global burn by about, global emissions by about 0.326 gigatons, which is roughly 1% of all global CO2. So that's a target that I think is very worthy, and that's actually why I'm standing here. I talked about the 50% increase in range. Now, if there's any flight dispatchers here, or people with experience with this, you know that if you drop your fuel burn by a certain number, then the range increases even more than that particular number. And I'm not just saying that for the fun of it. What I do here in this slide is I take an old A321 CEO, and I show you what it normally does with like 210 people. It's around 2,300 miles, call it, right? This is a typical payload range diagram. Now we take another A321 CEO and we modify the engines. And it'll do this. It'll do 3,600 miles, which is more than 50% extra. And that's a very interesting airplane now, because it's only 10% short of the A321LR. So just imagine that you roll this stuff out. It will have an impact on the entire industry, food chain. I'll take a few more steps because I think this is a very important point. So here we have a standard A380, very nice picture. Thank you for the sponsor. We know how much these airplanes burn. It's not a difficult calculation. Now, put the airplane away for an A-check, and you get it back with 4 modified engines, and that's all it takes, 1 A-check. We do the entire STC in an A-check. And then you have the delta burn effect, this is what we call it. And of course, the same story, much less fuel burn, much less emissions, etc. And 1.5% times the range. Now what can you do with 1.5 times the range? Does anybody know a project with an extreme range requirement? Sunrise. So I did some calculations. I like to do that stuff. And I created a LOPA in an A380 which mimics the LOPA that the A350-1000 is going to have. So it's a sort of balance between first and business and economy and everything else. We do an A-check again, we modify those engines again. And now we can fly a full A380 all the way from Sydney to London and take 15 tons of cargo as well. And this is an otherwise standard A380, just the engine modified, right? Those are not just the numbers. I ran the numbers with the performance model, and I actually increased the track distance because we have to fly around Russia. I also included a 20-knot average headwind because I could. And this is what it looks like. For those people who are happy to sit in the airplane for a day, this is what you're going to get. So, eye-watering numbers. There is a gentleman in the Middle East who likes to talk about the A380neo. We've tried to give him a call, but he doesn't answer the phone. We can give him his A380neo. All it takes is an A-check. Oh, and first he has to give us one for the STC. We'll do that. The ROI is 21 days, if you believe it. But by that time, we will no longer call it the A380neo. We're going to call it something else. The A380 Delta Burn. Where are we today? You know, why is this stuff not flying yet? Well, our limited funds allowed us to buy a turboprop. That is our test aircraft. It's a Merlin with the Honeywell TPE 331 engines. And we use that for the STC of the propeller. The propeller uses the same effect that we see on the fan blade, except it's not so dramatic. I mean, we only get like 20% of the efficiency. But again, the numbers that we get are eye-watering. We need to know exactly how much thrust we are producing to be able to compare like for like. And we developed this very interesting measuring tool that gives us the following data. What you're looking at here, the green line, is a run-up of the engine, you know, ground idle, flight idle, and they go all the way to maximum power, and then after that you go down again. So this is a typical power run diagram with a timeline at the bottom, and on the left, the y-axis is the thrust that the engine is producing, the engine propeller combination. On the right-hand side, you see the same, except that is the modified aircraft, engine. And you see that that's a very different graph. How different? Significantly different. There's all the numbers here. You will get a copy of the deck. You can take your time and look at it later. But the nutshell of it is equal thrust, both engines, right? With one modified, the other one not. The modified engine reaches the same thrust at a 45% lower torque, means lower energy input. And when you look at the difference between the max thrusts, that's 21%. But we arrive at a 21% higher thrust at an almost 20% lower torque than the other engine. So again, eye-watering results. And it's a testament to the aerodynamics that are applicable to both the propeller and the fan blade. Because after all, the fan blade is a fixed pitch propeller, right? We are bootstrapped. We're running on private funding and family and friends and stuff. So we are able to do this STC for turboprop, and we will get there, I think, by the end of the next quarter, maybe April, May timeframe. The fan engine will have to wait a little bit until we have saved enough money to do that. Of course, for an STC, you need to buy an airplane, you need to fly it. It's an expensive exercise, so we need to save a bit further. Unless somebody steps up and says, hey, here's my wallet, or says, hey, here's my airplane, use it, give us a cut of the STC, and we move on. And that is only to accelerate our program. If we do it organically, like we're doing right now, we will get to the fan STC maybe in about 2 years. If somebody helps us to accelerate, we can start decarbonizing today and not in 2 years' time. I told you I wasn't selling anything, but maybe I lied. I am selling something. Yeah. This is a happy snap selfie of part of our team. We were at a test cell in the UK, in Gloucestershire, the same test cell where they ran the Olympus engines for the Concorde. So they know something about thrust. We did this test cell, and we had a few people attending. The first person in the red circle is the inventor of our IP, the CEO of the company, Captain Peter Ireland. Brilliant guy. The second circle I want to highlight for you is a gentleman who used to be program director for the Rolls-Royce Trent 500 and 700 programs, and he was there as an independent observer. Third gentleman is a certification engineer with credentials with UKCA and with EASA and Alliance. And the fourth gentleman who doesn't get a circle but has a very big camera in front of him sits right next to me.
Me, yeah. I witnessed it. You come and ask me about it afterwards if you're skeptical. Because I actually saw it. I'm not joking.
Yeah.
It works, believe me.
Thank you. So like I say, our program is live and active. So the Rolls-Royce gentleman, he saw two things. He witnessed what we did to the fan engine, this thing, and then he witnessed the thrust results in the control cab, and he fell off his chair, like unbelievable. When we finally get to market, what's it going to look like for you guys? We're going to lease our STCs to the community, to airlines, business jet owners, turboprop operators, everybody. We will allow you to save first and then pay us, so you don't have to put money up front. We will do the installation, and like I said, it will take about an 8 check, and we will also run our own camo and do whatever is required to keep the modification in top shape. We will use some of your operational data to actually do the camo, and we see in the operational data whether the modification is still working properly or not. Design life is C-check to C-check or better. I mean, we haven't really tested this yet, but our initial testing will give us at least C-check to C-check. Then the company itself, as you can imagine, what we are talking about, what we are producing is quite disruptive. And The one thing that we are very afraid of is that anybody with a lot of people or staff gets access to our IP or our equity and becomes an activist investor who decides that only that OEM will get access and the other OEMs will not get access. So to prevent that, we have quite a unique structure in the company. We will never give away equity. Anybody who wants to financially work with us will have to accept the fact that it's revenue-based funding. We are open to win-win partnerships, and there are various formations of win-win partnerships. I'm happy to discuss them with any of you. I've done already with a few of you in the crowd. They are still smiling. What alternatives do you have in the industry today in terms of effects that we create and that we show and that we demonstrate and fly? So our friends at Rolls, they invested about $1 billion to make the XW engine about 1% more efficient. Well, I congratulate them with the 1%. It's a shame it had to cost $1 billion. Then the other project they have is the UltraFan. Also a lot of money, and then to have an engine that runs around 10% more efficient than the current XWB. And on top of that, it's only a forward fit. It only fits one particular airplane once it's finished. Our product is retrofit for each and every turbofan engine in existence today. Right? As long as the BPR is more than 2.5. In a recap, 1/3 aviation emissions reductions this decade. And the 50 STCs that we would like to do, we can do this in 5 years. By that time, the amount of SAF that is required over time will have reduced by 1/3, which makes it a more attainable goal for the world. Of course, we also help with known CO2 initiatives. You can imagine that our engines produce a lot less water. Condensation trails might be less. The particulates that would come out of the exhaust are more or less the same. However, we drop NOx by 50% because we have much lower combustion temperatures. So those are all additional effects with what we do. You can imagine that the electric club would be happy to have our props because suddenly that battery will take the airplane a lot further. Right? So we're working with them as well. We're talking to them. I just came back from a different event where I met some of the startups in the electric sphere. Good discussions. Our invention, our modification is the lowest cost, easiest implementation with the highest impact anytime. It's very straightforward and it's available today, but after the first STC. It's also a great investment and a great ROI. Like I said, we're a bit of a different company, but I'd love to have that discussion with anybody. And as a result, what we're trying to push is decarbonization in a way that the industry makes a giant climate leap. And improvements on that front are requested, they are expected. We see more and more social pressure to actually make flying greener, and that way we ensure that it stays relevant. Okay. We are in certification today, so this is not a hobby project, this is not a theoretical something. We are in certification and we're looking for that support to accelerate. And if we don't get it, we'll get there eventually. We had a talk with NASA about half a year ago, the steering committee on, among other things, the blended input design. And they told us that our work could well be the largest step change in aviation emissions reductions of the century. Again, this is not our text, this is their text. I have a lot more to tell, but thank you.
Very good. I have several questions here. I'll merge the first two, because it says, do aircraft manufacturers allow the modification? Did you already share this fan modification with any engine manufacturers? What is their feedback?
The industry is aware of what we're doing. There's a lot of buzz in the background. We have talked to Airbus, we have talked not directly but indirectly to Boeing. Rolls is very much aware of what we're doing because the gentleman was visiting. most of our discussions were at the level of introduction. This is what we're going to be, and we may need your help. As an example, if you modify thrusting engines in Airbuses, for instance, you need to work with some flight computers as well and stuff. So we will have to work with the OEMs at one point in time. But we don't have any direct activity with any of them. In terms of your engines, whether it's going to hurt your warranty or not, depends. If you still have warranty, that's the situation. Most engines don't have any warranty. Power by the hour, maybe it's okay. The thing is, if you play one OEM against the other OEM, all of them will always think about the fact that if I say no and they say yes, then they will be burning a lot less fuel and we will not sell any engines. So I think as an industry, it will come together, especially when the politicians get the good smell of this stuff. They will actually push for this to be implemented. It's the fastest, it's easiest way to get to decarbonization.
Okay. Question you always get every time you give this presentation, Sandra, why haven't the engine manufacturers done this already? I could answer it myself.
Okay, so each and every engine turbo machinery engineer learned from the same textbooks. In those textbooks, most things are possible and some things are not possible. There are hard limits to what you can do. What we did is we looked beyond the limits and we worked back. So we had maybe a more open mind than your standard hero engineer in OEMs. Again, what we discovered is nothing new. It's just never been applied to what we do. And our patent is pending. We keep it pending a little bit longer until we're satisfied that the SDC will be there and we can publish it. But once that patent is out, those textbooks will have to be rewritten. A simulation program like GasTurb will have to be re-edited for a new version, because if you go to GasTurb today and you try to replicate what we do with the fan blades, it can't do it because it hits certain physical limitations that have been programmed into it, because that's how the textbooks are also written. And that's the answer. We looked where nobody else looked.
Well, I think you told me before yourself when I asked this question that there have been some aerodynamicists and physicists that came close,
Yeah.
but slightly missed it.
There have been around 2,100 PhD papers on this subject, and 2 of those papers came close to what we discovered. However, in the zeitgeist then, late 80s, they didn't look far enough. They maybe didn't have the computing power to look far enough. Anyway, they stopped short of the end goal, and the end goal is this.
I'll give you a few questions you can quickly answer. I'll combine them, okay? Clement Seabot from Air. How old is this project? Do you already have customers with the modification implemented? Someone says, what's the catch? Someone says, how did you achieve success where others failed? Do you now, how the fuel providers may react?
Okay. Wow. Nobody is flying with this yet because there's no STC yet. Officially you cannot put something on an engine and just go fly. The only airplane in the world today that flies with this is our business jet. We have a Westwind business jet with Honeywell TFE engines. That one is modified. It's a private aircraft and we get special flight conditions every time. So it's not in the market yet. Yeah.
Have what? Okay, right. Someone's asked, did you already share this fan modification with any manufacturer? What is their feedback? Are we talking about geometry change on the fan blade? How do you intervene in the blade structure?
Sorry, second.
The system keeps ordering the wheel and right. It's lost the blade. Are we talking about geometry change of the fan blade? How do you intervene in the blade structure?
Oh, we don't. Sorry, maybe I wasn't clear. What we do to the fan blade is additive. We put something on the fan blade. And to the fan blade, what we do is transparent, meaning it's more flexible than the fan blade itself. So stresses-wise, everything else, the fan blade is in the same position it was before. What we put on the fan blade is in the range of 4 or 5 grams. It's nothing compared to the mass of the fan blade. We've flown our modification with half the fan disc modified and the other half unmodified. No problem. no imbalance, nothing like that. If we lose some of the applications during test flying, the effect stays more or less the same. You know, there's only a very slight regression.
Okay. Is the STC already certified with the ARSA?
No. Our base of operations is Phoenix in Arizona, because it's much easier and faster to work with the FAA. We haven't really talked to EASA yet. We've been visiting UK CAA. They are aware of what we are doing. They like it. FAA actually told us that for the propeller, what we're doing is a minor alteration. However, because it has such a large effect on the aircraft operation, we're doing an STC.
I think we'll have to be, this will have to be the last question because we're running over here. Do the low bypass ratio engines have greater benefits than high bypass ratio engines?
Well, in effect, what we do is we vastly increase the bypass ratio of the engine. We see an increasing effect with an increasing bypass ratio. And part of that is because there's a lot more fan area, and the other part is that the bypass duct has a much lower volume, so relatively it has a slightly larger, but you're talking about maybe 30% versus 34%, so it's still quite large for the lower bypass engines. Lower bypass engines are very difficult to work with because the enormous radial loads when the small fans are turning. And we spent 2 years in material science studies to get the right composition for our additives. And that was the hardest work on the smallest engine. That's why we set a lower limit of 2.5 ppr.
Right, Simon, thank you very much. I think I'll have to leave it there. Thank you.